Hi all, I am Sai Ashish Soumyajula and I am going to present my work, Token-Specific Watermarking with Enhanced Detectability and Semantic Coherence for Large Language Models. LLMs have demonstrated exceptional generational capabilities. As these models improve, distinguishing human-generated text from LLM-generated text becomes crucial. This identification helps in detecting academic dishonesty, spam, and misleading content. Additionally, if LLM-generated text is used to train other LLMs, it can lead to training degeneration, preventing models from learning new representations. Prior methods bias the LLM's output distribution towards a specific subset of tokens during generation. Consequently, detection becomes feasible by estimating the likelihood that the LLM's output exhibits this biased pattern. As illustrated in the diagram, the LLM is conditioned to generate text given a prompt. During this generation, the output distribution is biased towards a specific subset of tokens embedding a watermark. This ensures that the generated text contains the embedded watermark, facilitating its detection. Let us say, condition on cat jumped on the, we need to generate the next token. Say the vocabulary contains the tokens bed, moon, sofa, pen. Hash of the previous token is used as a seed to partition the vocabulary into red-green list with the splitting ratio gamma. Say bed and pen belongs to the red list and moon and sofa belongs to the green list. A small positive number delta is added to all the green list tokens to encourage their generation. Detection involves testing the hypothesis that the next token is selected without the knowledge of the red-green list rule, that is, without the addition of delta. Given the hash function, the number of green tokens is counted in the generated sentence. The z-score is then calculated by substituting the number of green list tokens in the generated sentence. If the z-score exceeds the threshold, we conclude that the text was generated by the LLM. However, this method faces the following limitation. Improving detectability by sufficiently shifting gamma and delta affects the semantic coherence of the watermark text. It lacks an adaptive mechanism to adjust gamma and delta appropriately. Take the example sun rises in the. The next token is east with certainty. However, high delta and low gamma might not select east. If low gamma is used, fewer tokens are chosen for the green list, reducing the chance of selecting east. Moreover, having a high delta further decreases the probability of choosing east as the next token. To address these challenges, we propose to learn token-specific splitting ratio and watermark logic, that is gamma t and delta t. Given the prompt and the generation till now, we take the embeddings of the previous token and pass it through a gamma network to generate gamma t, that is the splitting ratio for the next token. Similarly, we pass the embeddings of the previous token through the delta network to generate delta t. This delta t is used to bias the green list tokens while generation of the tth token. We get the splitting ratio gamma t from the gamma network. For each token v belonging to the vocabulary, we sample yv from a Bernoulli distribution parameterized by gamma t. If yv is 1, then the token v belongs to the green list, else it belongs to the red list. Gumbel softmax trick is used to make the sampling process differentiable. Next, we calculate the modified logits by biasing the logits of the green list tokens using delta t. Observe that yv indicates the token v belonging to the green list or not. Thus, it is used to scale delta t appropriately. If it belongs to green list, then delta t is added, else it's not. To train the gamma and delta network, we use the following objective functions. First, in order to improve the detectability, we propose to use a detection loss. We propose to directly optimize over the z-score to improve detectability. So we first proceed to derive the z-score based on the distribution that utilizes token-specific gamma t and delta t. We make use of the following theorem to derive the z-score for this distribution. Consider t independent Bernoulli random variables, each with means mu1, mu2, so on mu t. The sum of these variables follow a Poisson binomial distribution. When T is sufficiently large, the mean of this distribution becomes the summation of the means, mu's, of individual Bernoulli random variables. And the variance is sum T equal to 1 to T, mu T into 1 minus mu T. Applying this to our context, each token can either be green, that is 1, or red, that is 0, following a Bernoulli distribution with mean gamma T. The total number of green tokens is the summation of these Bernoulli random variables, forming a Poisson binomial distribution. Thus, the modified z-score is formulated using the mean and the variance of the distribution, assuming T is sufficiently large. We propose to directly maximize this objective to improve detectability. However, number of green tokens in this text is non-differentiable with respect to gamma t and delta t. Thus, we propose a surrogate function where PGR is the probability of selecting a green token. We maximize z hat or minimize the detection loss, which is minus z hat, or the surrogate function which we just derived. Next, we propose the semantic loss. We generate the sentence embeddings of the text before and after watermarking using the SimCSE model. We then propose to maximize the cosine similarity between these sentence embeddings. Alternatively, we propose to minimize the semantic loss, which is the negative of the cosine similarity between these sentence embeddings. We propose to optimize these objectives using a multi-objective optimization framework. This is because we are optimizing over two competing objectives. A multi-objective optimization framework estimates Pareto optimal solutions, which are solutions where no objective can be improved without degrading another objective. We use the MGDA algorithm to solve for this optimization. So this is our proposed method. Let us dwell into the experimental setup. We use the C4 dataset for our main experiments with 6,400 training samples, 500 validation samples, and 500 test samples. The z-score is set to maintain the FPR at 0% and 1% empirically on their respective test sets. We compare our method with various baselines. Our approach performs better than others at 0% FPR and also at 1% FPR. Our method further outperforms EXPEdit, which is an indistinguishable method. EXPEdit does not have a delta parameter to vary and plot the curve, so we present the results as a table. Moreover, EXPEdit is restrictive and cannot be used with any decoding strategy that the user wants, for instance, the beam search or the greedy search. Our method achieves higher speeds than the EXPEdit, SIR, and multibit, while achieving speeds comparable to KGW, sweet, and no watermarking. Further, we directly apply the trained gamma and delta network on the OPT model to the Llama 2 models of various sizes, that is 7B, 13B, and 70B. Our method outperforms KGW across all model sizes. We also evaluated our method when subjected to various attacks to remove the watermark, such as the Dipper paraphrase attack and the copy-paste attack. Our method performs better than KGW under these different attack scenarios. So these are the main results. Please refer to the paper for detailed results on different generation lengths, different data sets, other different attacks, comparison between theoretical and FPR, empirical FPRs, and other additional experiments. So I would like to conclude that we propose a method to adapt the watermark strength based on the semantics of the previous token. We propose to use lightweight networks to output token-specific gamma t and delta t. We further propose two different classes to improve the detectability and semantic coherence. Differentiable surrogate of z-score metric is proposed for direct optimization to improve detectability. We optimize the network in a multi-objective optimization setup to improve both detectability and semantic coherence that are competing objectives. We perform extensive experiments to evaluate the efficacy of our proposed method. With this, I conclude my presentation. I look forward to engaging with you at the poster presentation session for more details and discussions. Thank you.